All right, so we're going to change this. I apologize for the typo here, but suppose only 5 students have a driver's license. Should we be surprised? Okay, so the first thing you recognize here is everything that we've done so far has been in percentages, and now they're asking you about this number. Okay, so let's change this number to a percentage. I think you'll find on some of the homework I go back and forth because I was kind of finding my way still, but I'm like, yes.
Sorry, I was so the SD like the standard deviation is really 6.4%. You said everything's in percentages, or no?
No.
Oh,
Um, oh, I see what you're saying.
because that would be 30.
We could do it either way. It works out the same.
Okay.
Okay. So typically we do, and that's what I was going to say. I sometimes do percent, and sometimes I do the proportion. Sometimes I actually do the whole number percent. Sometimes I do the point whatever.
Mm-hmm.
Try not to let that bother you too much. I apologize. So if it's 5 out of the 50 students, well, that's point one, right? So we know that this normal model applies. I've got this normal model where the mean is 0.3 and the standard deviation is 0.0648. And I want to know what's the probability that my observed proportion, p hat, is less than or equal to 0.1.
Oh,
So here's 0.3. What's the probability that we're going to be in here less than or equal to 0.1? And that's how you show your work on the AP exam. You tell them I'm using a normal model and tell them I'm finding this probability down here in the left-hand tail. Okay? So you can either do that on the TI as a normal CDF, or you can do that on the NumWorks. Let's do this. I always forget to minimize that. If you minimize it, it makes it a lot easier to use for something else. All right, so let's go back. It's a normal model. The mean is 0.3. The standard deviation is um,
yes.
0.0648.
Yes.
Thank you. I want the probability that this is less than or equal to 0.1. And that's 0.001. So less than a tenth of a percent chance. So yeah. The probability of this happening some days is about 0.1%. That's not very likely. Now, quick question for you. Could it happen?
Yes.
Absolutely, it could happen. Okay? So, what would you likely do if this happened? Yeah, my first response would probably be that. Let's do another sample. Let's throw this one out. Let's do another sample and see what it comes out to be. If it came out to be, you know, similarly small, what would you suggest then?
Your mean is wrong.
Yeah, the mean was probably wrong. I would question, you know,
It's really 30%.
is it really 30%? Okay. This is an idea that we're going to use later on in this uh, section. What you're going to do is you're going to be given a sample of a particular size. You're going to find the mean, and you're going to have something. There's some claim that the proportion was this, or that the mean was this, and you're going to find out. All right. Well, how likely, if the stated is correct, you know, what's the probability that I would get this kind of a score? And then you're going to go, you know, I don't think I believe that. Okay. It's called, it's testing, right? We're testing a hypothesis. Someone says, I think that in this school that 30% of the students have a driver's license. If I did this, I would go, I think you're wrong. Okay? And that's where this is leading. Okay? All right. So that's proportions. We can also look at the sampling distribution of a mean. So the sampling distribution of any mean becomes more normal as the sample size grows, as long as the observations are independent and are collected with randomization. So that means we need to follow the 10% rule, and we need to have things, you know, randomly selected. The interesting thing about that is it works even if the population distribution is skewed or binomial. Okay? And I remember struggling with this for a little while when I first did it. So here's what we've got. We're going to go through this kind of slowly. This is an entire population of something, very much right skewed. Has a mean of 14.05 and a median of 10.7. That's a pretty good clue when those are that far apart that this is going to be skewed to one side. And the standard deviation is 11.82, blah, blah, blah. Okay? So what we're going to do is we're going to take samples, and we're going to take samples of size 30. Okay? And so I did that once. And that shows here. This is just one where I've taken a sample of size 30. So then I'm going to take the average of my sample. And I'm going to put all of those on a graph, and it ends up looking like this.
So you took one group of 30 from
All right, I took a sample of 30,
the population.
found the mean of the sample.
Okay.
So I found the average of the sample. So after I've done the sample, I only have one number for that sample. It's just the average.
Okay.
Okay? And then I do that over and over and over and over again.
Oh, and so the mean is what's represented on the second graph.
Yes,
So
the
like
mean of
each
that
little-
sample.
Each bar. And then the number on the left side is how many times that mean occurred.
Correct. That's the count.
And so how many samples of 30 did you do?
1,000.
Oh, okay.
That's in this next one. We did 1,000 samples
Of 30.
of, we did samples of size 30, and we did that 1,000 times.
And you found the mean of each of those.
We took the mean of each sample, and now we've plotted those means as a histogram.
So what's the difference between the second and third graph?
This graph is just, I have taken 30 samples, and I have found the mean, and I have just plotted the mean of each of the, I've taken 30 samples, I found the mean of those, of each sample, right?
Yeah.
Now I'm going to take the mean of that sample. I'm going to take all of those sample means and put them together. So I took a sample of size 30,
Mm-hmm.
took the mean.
Put it on a graph.
Yeah.
Did that 1,000 times.
Yeah, now this isn't the whole 1,000.
Yeah, that's why I was confused.
Yeah.
Okay.
Yeah.
But
This-
that's some of them. And
Right.
then after that, you took.
We just
all
made a
of-
histogram of all of those means.
Oh, okay.
So if you do a histogram,
And then you found the means of all of the means.
yeah,
Oh, okay.
So the first one's pretty much just like a dot plot in a sense, but just without the dot.
it's not a dot plot.
Oh.
So that's why the standard deviation is way smaller on the second one?
Yes.
You're taking the mean of means.
Yeah.
I get the second graph, I just don't need the bigger one.
So the third one, what we're going to do is so this is one sample,
Yeah.
okay? And so there are 30 of them. And then I'm going to take the average of those.
So there's 30 samples of 30.
No,
Just one sample.
I have taken 30 individuals.
Yeah.
Here are the individuals. Okay, so this is the individual. So we're not doing a mean of a mean.
Not in that one, but in the
We're not doing it.
Oh.
No. So what we're doing is this is a sample
Yeah.
of 30.
Yeah.
This particular sample, the mean is this, the median is this, the standard deviation is this,
Yeah.
right? So we're going to take that, just the mean, and now we're going to do that 1,000 times. So we're just taking the mean from this sample, and then we're going to put that on here, and then we're going to do that 1,000 times. We're making a histogram of the means of the samples.
That makes sense.
We call them the sample means. I know it can get really,
Do you put the like 30 samples back, or you go back to?
yeah, you always replace.
And then mix it up and choose 30 more people from the population.
Yep.
Take that mean, put it on this third graph, and then do it again 1,000 times.
Yep.
Okay.
Yep. So this is just a single sample.
Okay.
And its mean is this. And you notice that the sample, the mean of that particular sample is not particularly close to this mean. It's not terrible, but but if I do that over and over and over again 1,000 times,
Closer.
I get something that's really close to the original mean. So this is called the sample means.
That makes sense.
Okay?
What are the numbers on the left side of that? Oh, that's just how many.
That's
samples.
the count.
Okay.
How many times did that end up being the mean?
Mm-hmm.
And it's a histogram, so I've got little bins.
Yeah.
It's not how many times was it exactly 14.9265? It's within this little range.
Yeah.
Yeah, that makes sense.
Okay? So when you take the sample means, you're like, oh, well, if I'm taking a sample of size 30 and I do that often enough, this starts to look like a normal graph.
Yeah.
It also turns out to work even if your original population is bimodal. Okay? Just a real quick aside, this is another way that people can lie with statistics, because what they can do is they can show you this and go, oh, well, the average is normal. It's fine. And you're like, but you don't know that the original data was really badly skewed.
Mm-hmm.
Yeah.
Okay? So, it leads us to a useful idea called the central limit theorem. Which says when a random sample of size n is drawn from any population with mean mu and standard deviation sigma, it means that y bar, which is the average for my sample, has a sampling distribution with the same mean, but whose standard deviation is given by the standard deviation of y bar, and I wrote it as SD also for standard deviation, is equal to the standard deviation for the entire population divided by the square root of n. So what happens is, the bigger your sample is, the smaller that standard deviation gets.
The bigger sample is, the smaller the standard deviation gets.
Right, because the denominator is bigger. Okay, now there's diminishing returns with that. You know, you're never going to be able to get this to be zero unless your sample size is enormous. And if your sample size is too big, we have a problem with independence. Okay? So no matter what population the random sample comes from, the shape of the sampling distribution is approximately normal as long as the sample size is large enough. The larger the sample size used, the more closely the normal model approximates the sampling distributions. All right, so when can we use this? Well, the data values have to be sampled randomly. That's always something that we assume. The sampled values must be independent of each other, and this is where you can't have too many, so we'll again use the 10% condition. Okay, the sample size, it must be big enough. How big? Well, it really depends on the shape of the population distribution. If we go back up here, if this is really, really, really badly skewed, like, you know, it's got a tail that's over here, you're going to need more. And if it's bimodal, you need more than you would if you didn't. So typically, and I don't know, this came from somebody who wrote an article and he said, yeah, 30 ought to be enough. And ever since then, statisticians have glommed onto that idea, and that is sort of the gold standard without any really good mathematical reason. But we all kind of nod our heads and go, okay. All right. Y'all have a good day. Thank you.